enhance your webinar experience, please enjoy this housekeeping video on how to utilize the tools this platform has to offer. Please note, we will follow up after this presentation concludes with webinar material and resources.
Well, good morning, everyone, and welcome back to Innovation Underground. I'm your host, Graham Bain, lead of the subsurface innovation team here at Enverus. And so when we look at the future energy mix, I think the biggest missing piece of the puzzle is often reliability, finding power source that's scalable, low carbon, and capable of providing true baseload around the clock energy. Today, we're diving into advanced geothermal systems, or AGS, and the potential for closed loop technology to solve that problem. I think there's a heating component in there as well, which we'll talk about. But to make geothermal work at, I think, a global scale, we need the right people. There's a massive network of talents, subsurface expertise in the traditional oil and gas sector that's perfectly suited, I think, to unlock this new wave of energy. And I'm lucky enough to be joined by one of them that I think exactly intersects that sort of transition here. And he's an engineer who spent 7 years, correct me if I'm wrong, pulled that off LinkedIn, in the Canadian oil sands before pivoting to both founding and leading one of the most exciting names, I think, in the geothermal space. So joining me today is Matt Toews, the Chief Technical Officer at Eavor. So thanks for joining me, Matt.
Thank you for having me. Happy to be here.
Awesome. So, I know there's a lot on Eavor's technology and, progress that you've made in Germany, Everlight, which is really exciting, and we'll dive into that for sure. Mm-hmm. But I think before we do, I'd love to start off with, the person behind that, or one of the many people behind that who made that happen, mm-hmm. which is yourself. There's a lot of people that I speak with on a daily basis that are always curious how they've transitioned their skills from oil and gas to things like geothermal, and you're a great example of that. So I know you spent your early part of your career in the oil sands, a reservoir engineer, designing and sort of some of the SAGD operations up there. And so maybe take us back to that time in your career. What was the moment that you decided to pivot from hydrocarbons to heat?
Yeah, absolutely. Well, I think, for me, it was a bit of a fortuitous timing of a lot of different things coming together. I've always been entrepreneurial. I always wanted to start a business, and I had, that time, it was tough. Oil and gas is always up and down, but there was a tough few years there. Yeah. And then SAGD, around 2016, 2017, things just weren't growing. And if you're in a company and it's shrinking, and it's static, and it's not dynamic, you're not building, it's not as fun. Yeah. So there's this, I was like, okay, well, now is a good time. I'm not having as much fun. And I loved building SAGD projects. I love solving the technical challenges. I love deploying the technology. And, I had this skill set that I knew was useful in geothermal. So it just seemed to make a natural fit. And I met some other people through networks, and we decided to join up and found Eavor.
Cool.
And yeah, and that's basically how it happened. No, it's not. Yeah. Not any more complicated than that.
Yeah. No, I mean, I get that time. I graduated university in 2014, mm-hmm. which was a pretty unfortunate time to be entering the petroleum industry as a geologist, and it's very long duration of hard times for sure. I ended up at the Alberta Energy Regulator, actually working SAGD, looking at sort of different operators, developments, and doing reserves and things like that. So I'm sure there's a lot of things we could talk about on the SAGD side.
Totally.
I mean, I'm curious, are there like what are the biggest parallels that you see between, say, SAGD and geothermal?
You know, there's so many. I think, you know, first of all, SAGD's, you know, a lot of people call it a resource play, and it's similar in that way to, say, tight gas or shale oil or tight oil, where you basically know where the resource is. And in SAGD, it's so shallow that there's so many wells, there's so much seismic data, you really are not exploring for the resource. It's not an exploration game. It's about deploying technology, engineering, and manufacturing it out of the ground and driving down costs over time with scale, with improved operations, with improved technology. And that's basically what we do, right?
Yeah.
We're not looking for a resource. We are just using the natural thermal gradient of the earth. You go deep enough, it's hot everywhere in the earth. If you go deep enough, so we know where the resource is. It's you know, relatively easy to kind of characterize it for our approach. And so then it's about applying technology, manufacturing it out, driving down costs with scale, with a learning curve, and with operations and technology. So it's very parallel. And if, you know, that's why the company, we have dozens of people working, you know, 90% of them are from oil and gas. Yeah. And most of that is from this kind of resource mindset of oil and gas, where it's very, very similar.
Yeah. So that's really cool parallel. Like, I'm sure it's very different from other approaches, other geothermal, well, traditional geothermal approaches where you're looking for a resource specifically, and there's a big component of exploration and that exploration risk and improving exploration, whereas this is more like the resource is there. It is everywhere. There's heat beneath our feet, you know, to that many times. Yeah. And it's like, how can we engineer it out? And I think what we've seen in the oil and gas space, which I know is being replicated in the geothermal space as we speak every day, I mean, you're a great example of that, is that we're really great at engineering our way to better production and to better results and to lower costs. And, you know, SAGD is a great example of that, from mining the oil sands to getting it out with steam to unconventional oil development, where, you know, we've just gotten so good at hydraulic fracturing, where it's like we can just manufacture. And it's almost the same thing with unconventional oil. It's like people don't really care about the resource anymore. It's just like, how do we engineer more oil out of this rock? We know that the shale is there. So that's I think that's a really interesting parallel.
Yep, absolutely. And the other thing that, in my specific case, is the skill sets, the technical skill sets are similar. You know, SAGD, it's thermal well design, you know, long wells, thermal facilities, thermodynamic modeling, simulation. All that is what we do here, but in reverse. Instead of injecting heat in the ground, we're extracting it.
Yeah, totally. So that's great. I mean, I'd love to hear folks' backgrounds and how that has taken them to some of these energy transition technologies. But, you know, maybe enough about you. We'll talk about you for a while. You're a very interesting guy. But I think the reason why people are here to learn about the technology, to learn about geothermal itself, to learn about what Eavor is actually doing in the geothermal space. There's been some recent news on the startup of a project in Germany. I have a lot of technical questions that I'd like to ask, and I'm sure the audience would. I forgot to mention the beginning, audience. There's a question box. We'll try to take questions at the end. Matt has said he would like to take some questions.
Anything.
Anything. He's open to any question here. So put it in, and we'll get to it. If there's we'll get to as many as we can, I guess. After my questions, I'm going to be greedy and take the first ones. So yeah, I mean, getting into the meat of it, like, you know, we've gone from these conventional geothermal systems, which have, you know, been around for hundreds of years, or at least 100 years. We speak, you know, Italy, I think one of the first real geothermal projects, to, you know, a lot of, I mean, I wouldn't say a lot of installed capacity in the United States. I think we're over 4 gigs, but that's all from conventional resource. There's issues with that in terms of exploration, and I think it's getting harder and harder to find those resources. You know, people think of Iceland, which has a very, you know, it's a very fortuitous location where they have a very great geothermal gradient. The country is pretty much almost entirely powered by geothermal, but there's a lot of new technologies evolving, and which I think is really exciting in terms of the scalability of geothermal, the modularization of it, and the ability, as you mentioned when we were talking before, at least, to do it everywhere, right? You know, the constraint before was we need the resource, we need to do it in a spot where the resource is, which may not be close to transmission or close to population, which is obviously a huge problem, and that's all changing. And you know, Eavor, I think, is taking a really unique approach to that in terms of your closed loop design. And so I'd love to hear it from you, like, you know, in your mind, what are the differences between, say, if we talk about conventional, enhanced, I don't like to call them enhanced and advanced, I like to call them engineered geothermal systems, as they are, where you have, you know, hydraulic fractured style and not. But I'd love to hear from you what the differences are.
It's actually getting hard to categorize because there's almost like a Cambrian explosion of different approaches and different ideas and startups and established companies, and you know, it's hard to keep track of it all, to be honest. So yeah, there's a lot of different. It's an interesting time, but I can speak about what we're doing. I mean, our approach has really been, our vision has really been the same since the very beginning, which is, let's build this closed loop system that's essentially, it's a radiator underground. It's a subsurface heat exchanger. It collects heat and extracts heat from thermal conduction from a mass of rock or a volume of rock. And then we circulate water, you know, a working fluid, but it's water with some additives through this system. And it passively picks up the heat, and then we use that on surface. So we either use it for district heating, or you can convert it to electricity, or you can do other things with it. And I think the main difference with our approach is it's a very, you know, we're trying to get to an area where it's a reliable, predictable manufactured product. Think about a solar panel or something like that. That's really what we're after. And to do that, you have to kind of eliminate the geological uncertainty, the dependence of the system on the specific kind of, you know, in geology, there's, you know, millions of degrees of freedom, and it's really hard to understand what's down there. So our system kind of eliminates that geological impact. And then it's very, once it's built, it's very predictable and very reliable over decades. So, and that's an important differentiator, because that it changes how you finance things, and it changes how you approach project development when you're certain, okay, I can just go do it here. I know what it'll cost. I know what the output is. It changes a lot of the way that you approach the market, approach the industry, approach the financing of these projects. Yeah, so that's what we're doing. We don't have any, you know, fracking. We don't have a reservoir, really, so to speak. We have a network of pipes. We don't have, you know, we have very small water use or water loss, and don't have induced seismicity. So those are some of the kind of softer stakeholder benefits that also are important in certain areas.
Yeah, cool. I'd love to pull on many of those threads.
Okay. Where do you want to start?
Yeah, I mean, first of all, you've had your project in Germany turn on, delivering power to the grid for the first time. Can you tell me just a little bit about that, and I'll get into some of the maybe details?
Yeah, sure. So, I mean, we started this project in Germany. You know, the whole justification, the whole business case around that was a first of a kind project to demonstrate the technology at a real commercial scale, and to prove that it can be economic in our, you know, sometimes we call it a beachhead market, or our first key market, which is the district heating market in Europe. And you know, the project just, the first loop has come online in December. It's generating heat. It's, we're generating electricity at the asset. It achieved what we wanted out of it. It was, you know, when we set out with that project, we had done a whole bunch of testing, and we built a pilot here and operated that pilot for 5 years here in Alberta. We called it Everlight. And we thought it was going to be, you know, it's classic entrepreneurial kind of, you know, we were a bit naive. We thought it was going to be pretty easy compared to, building on the experience that we had.
Yeah.
It turned out to be way more difficult than we had imagined. It was very challenging operationally, technically, setting up an organization, a team in a different country.
Yeah, totally.
Just all these different aspects, financing it. So it turned out to be a lot harder than we thought, but we have got it completed, and we have solved our technical challenges, and we have a really exciting future now in that market.
I think it is nothing short of amazing what you guys have accomplished with that project. You mentioned Everlight, and now you've got essentially the first version of your commercial loop. What are the differences between the two? There's a few things I want to pull. What are the differences between the two? Like, what is the difference in the configuration? And then maybe what were some of the biggest technical challenges that you ran into, say, drilling in Alberta, where we drill a lot of wells, versus drilling in Germany, where there's probably less expertise on how to drill the rock over there?
Yeah, sure. So I guess just from a kind of specification point of view, what we did in Everlight was it was 2.5 kilometers deep, and it was 2 multilaterals drilled kind of in parallel with each other, and we have an inlet well and an outlet well that are separated, and then we had a pipeline connecting the surface sites. In Germany, at the Gerets Ried site, we're going 4.5 kilometers deep, so almost much deeper. We're drilling from the same site with 2 rigs operating the same site, and the lateral lengths are 3,000 meters. And we drill these multilaterals off of the mother bore, and and then we intersect them using magnetic ranging at the toe.
Yeah,
and that difference in depth and that difference in scale, you would think, and we did think, to be honest, that it was not going to be that much more challenging, but it turned out to be a lot more challenging to do it at that scale, at that depth. And that's before we even bring in the kind of supply chain and challenges working in Germany. I mean, I think the German service industry, they actually have very high quality equipment. They have high quality people.
The Germans, of course.
Yeah, and they have good expertise, but it's just not as competitive and not as active. In Alberta, you need a coiled tubing unit. You can get one in a couple hours, and you could, in Germany, it might take you 3 weeks.
Okay.
So things cost a lot more when you have problems.
Time is money.
Yeah, and in drilling, time is money, and so there's when you have challenges in drilling, which is par for the course, then they just become a lot more expensive to solve them.
Yeah. I know you made a lot of improvements in terms of drilling. Like, obviously, drilling is a huge component of the capital cost in any geothermal project, which relates to drilling speed.
Yep.
Like what is the difference between, say, drilling the first well in Germany versus the last?
I mean, it's huge. So if you think about an Everloop, constructing an Everloop, we sometimes call it unit operations. So you drill the vertical well, and we set the mother bore, we case and cement that in place, and then we're splitting all these multilaterals off of that.
And the Gerets Ried project is 6 multilats on top of 6.
It's 6 multilats off of the like the inlet mother bore, or the inlet well case well bore, and 6 off of the outlet or a production case well bore, and then those individually intersect 3 kilometers out laterally, and so we call it has 6 lateral pairs, right? Because they're kind of pairs that intersect. And so the fluid water, when we're on production, goes down the inlet, splits into these 6, goes out, does a U-turn at the toe where there's the intersection point, and then comes back, and then up the production well. And so, there's a lot of challenges in doing that. Some of the things that went really smoothly was a lot of the aspects with our technology. And, we went into this, we have these risk assessments, like you do in any project where you have, where you have good project manager on it, you identify all the risks, and you have mitigation plans for them, and you estimate what your biggest issues are going to be, and you put a lot of effort into that. And we had, the intersections, the magnetic ranging intersection points as a high, risk. Well, that turned out to be actually that went smoothly. We deployed brand new technology there. We're ranging while drilling the first in the world, and we're doing that in a very quick manner.
Which is incredible,
Yeah.
because what are you thinking of from like the actual, inlet of the wellbore to the end of that wellbore, what, 4.5 kilometers deep, plus the lateral is
Yeah, so it's 8 kilometers.
8 kilometers, and you're hitting the target. That's,
which
is what's the diameter of
8.5 inches.
at 8.5 inches? That's like, I don't even know what an analogy for that is on the surface.
Yeah, it is pretty remarkable. But anyways, to get back to your original question, this is a long-winded response.
That's great.
Where I was going is, we have these operations, we call them unit operations. We have the sidetracking operation. We have drilling the lateral itself, the drilling or tangent operation, or whatever you want to call it. Then we have the ranging and intersection operation. Then we seal it afterwards with what we call rock pipe, and it's our chemical sealant method. And these are all different operations. But if you look at just the drilling one, the most recent wells, 3 of the 4 most recent legs that we drilled there, we did in a single run. I think the best was 8 days.
8 days.
And when we started, it took us 100 days.
Oh my God. So yeah, like 10 times reduction, not more. That's incredible. So that's going to directly relate to cost. And I'm sure there's improvement, or I'm sure you can bring that down. Like, what would be, say, the limit of?
Well, there's definitely room to improve from there.
Yeah.
But we see that more incremental improvements. We think we'll have a 10% improvement every few laterals, or every doubling of capacity, we'd have a 15% improvement.
Yeah.
So we think, there will be improvement, but we don't see kind of huge step changes. Where all the step change comes from for us is going deeper and hotter.
Okay.
So, our main thing that we're focused on is dollars per megawatt hour. And the way to drive it down is you increase the megawatt hours. Yeah.
Okay. Which is temperature and flow rate, maybe it's a big one.
Yeah, it's temperature. It's really about the temperature of the rock. Yeah. And for us, we're focused on geothermal anywhere. So temperature of rock basically means depth.
Yeah.
Yeah.
Maybe I'll pull on that thread on the temperature of rock. Like what temperatures are you targeting? What temperatures do you want to target? And then if we talk about the conduction side of it, trying to pull heat out of the rock into the water, I think thermal decline is a big question that comes up a lot, right? With any geothermal project, how long can this actually last for, and how do you increase that duration? But I guess on the first one, series of questions here, temperature, where do you want to go? What's thermal decline like?
Sure. So, the project that we're doing in Germany, it's in an average geothermal gradient. It's not like the Western US where you have these very high localized, gradients that are good for conventional geothermal, good for EGS, where you might have 50, 70, 100 degrees Celsius per kilometer as your geothermal gradient. Where we are in Germany, it's 30 degrees Celsius per kilometer. That's very comparable to, say, Alberta. It's very comparable to many areas of the world. It's an average geothermal gradient. And so at 4.5 kilometers depth, we're, roughly 155 degrees Celsius or so rock temperature. That's the first project that we're operating. And so we've already learned after our first loop that we've constructed and brought online, we're confident we can go deeper, we can go longer on the laterals on that project in Garrett Street. And we'll be placing those depths, deeper and longer over time, and getting hotter and hotter and hotter. And eventually, we think we can unlock geothermal anywhere, which is essentially you take an average geothermal gradient and you can produce electricity at a competitive price nearly anywhere in the world.
Yeah.
And you just need to get to the sufficient depth.
Yeah.
Yeah.
Cool. I think the geothermal anywhere component and the competitive pricing are obviously the big ones. But I guess sort of off the backs of temperature, what sort of thermal declines are you seeing in the reservoir? And how do you make sure that your reservoir declines as slow as possible and you keep that, project operational for as long as possible?
Yeah, so for closed loop, it's all types, and there's a few varieties of closed loop, but for closed loop, for Everloop, it's a very predictable process. For example, at Everlight, we predicted what the output would be over 5 years, and we're ran it for 5 years, and we're less than 1% different.
Yeah. So you've got a good, good pilot.
Yeah.
To draw information from.
We have a good pilot to draw information from, and I mean, I'm a, ex-reservoir engineer. So when you're working with reservoir performance, like having a variability in your forecast in year 5 or year 10 of 30% is like, that would be good, right? So
1%,
having 1% or less over 30, 40 years, it's really kind of unheard of.
Yeah.
And so the predictability comes from, there's very low degrees of freedom, or there's very low uncertainty. There's a low amount of input variables that actually change the way the system performs.
Yeah.
So so we have very predictable, long life, for decades and decades and decades, and you can bank on it.
Yeah.
And the way that and I think a lot of people get, I think, maybe a bit confused, or they say, well, there's a big decline at the beginning. I guess it always depends what you consider your baseline. So when we plan a project, we predict out the performance of the project over 40, 50 years. Right? And if you looked at the decline from the first minute to the, first hour, it's steep. And the first hour to the, the 24th hour, it's steep. But if you look at it, the first year to year 5, it's only like 15%.
Oh, wow.
And in year 5 to year 30 is like another 10% or something like that.
So there's some point of sort of state of equilibrium that you reach at some point. Yeah.
Yeah, exactly. And so we plan, you build a financial model and you get investors into it. And what they're looking at is essentially the average production over 30, 40 years.
Yeah.
And it's pretty flat. It varies from year 1 to year 30 only by, less than 30%.
Yeah, that's incredible. I think there's something you said about, very long life assets like that have a lot of value, and geothermal is excellent.
Yeah, absolutely.
Candidate for that. I'll pull on that thread in a second, but there's a couple more on the actual technical side of the project. I think one of them is water loss. I know a problem with traditional geothermal systems and even some enhanced types is water loss, and there's been some projects that have run into those issues historically with that. You mentioned rock pipe, which I'd love to hear more about, but also sort of how are the wellbores designed? I'd say there was a question that Chad asking what kind of OCTG you use for the motherboard. If this is a 40, 50 year life asset, it's probably has to be some corrosion resistance baked in there, right? But then the rock pipe and water loss, because if it's not, I understand that you're injecting some kind of cementing material in there to cement up the porosity.
Yeah.
And what is the water loss like in that, say, for a Garrett's Reed style project?
Yeah.
So 2 questions there, I guess.
Okay. So the first one, I guess, maybe I'll talk about the water loss first. So, we build this system, we drill all the multilaterals open hole. And then rather than case them, because
it's a lot of casing.
That's a lot of casing. It's expensive. It's difficult to actually put in. There's risks, a lot of risk associated with it. There's kind of these outlying risks that you get stuck installing in your whole well loop is screwed pretty much.
Yeah.
So there's kind of a whole series of costs and risk, and they actually putting in casing actually reduces performance because it adds a barrier. So we drill them open hole, and then we seal them with what we call rock pipe, which is a chemical sealant that is embedded into the porosity of the rock. So it's not like it's a film on the ID or the interior of the wellbore. It's embedded within the near wellbore space in the porosity of the formation. But it's not perfect. It's not a perfect seal. So we have water loss. I would say it's between 0.01% and 2% is how we expect it.
Yeah.
And that really depends on the initial permeability of the formation. If you're in, say, a basement rock, if you're in granite, it's going to be very, very low. Less than 0.1%.
Yeah.
Of the daily throughput.
Wow. Yeah, that's incredible.
Yeah. So it's low. That's a couple of orders of magnitude lower than other kind of more open systems.
Yeah. Yeah. I mean, it makes sense, right? You're going to get some loss and fractures and the permeability that exists.
Yeah. What was your other question was on the...
Yeah, the well construction, like
Yeah,
the actual architecture of the well part itself.
Yeah, so I mean, we have basically up until, so we have this cased well bore, and we split all the multipliers, and that sometimes we call it the cased mother bore. That is essentially a standard well construction.
Okay.
You'd see that in oil and gas, you'd see that in traditional geothermal. We learned a lot of things about that, which I can get into the details of, because I think it's one of the biggest problems we had and challenges we had that cost us a ton of pain. But that motherboard is very important to get it right. But ultimately, it's standard technology. It's standard metallurgy. And what we are doing is, because we're circulating essentially the same volume of water over and over, is we put corrosion inhibitors inside
okay. Yeah, I guess you can control the water. Totally.
Yeah. So we're doing that today at Garrett's.
Yeah. No, I mean, that makes a lot of sense. And that's maybe a huge advantage you have with the closed loop, is you can control the water chemistry.
It's a huge advantage. It's a huge advantage at the stage we're at now, because if you look at historically at hydrothermal or EGS historically, water treatment and water handling is a huge part of the operating cost.
Yeah.
We kind of eliminate that part of the operating cost. But where it really becomes a big advantage is when we start talking about super hot and super hot rock, because producing at at the conditions of super hot conditions, some of these casing strings get worn out or corroded in hours and days. So it becomes, I think, a bigger advantage as we go much deeper and hotter.
Yeah. I think that's an important piece to pull on. And I was gonna talk through this eventually, but it's around the operational cost. And I think that's one big maybe misconception with a closed loop style system, and maybe one that I was surprised by as well, is just like how low the operational cost is compared to the total upfront capital. Like, it's obvious that an Eavor style project is pretty capitally intensive up front. You got to drill a lot of wells to make this happen. You talk about 40 or 50 or even more years with very low operational cost. What does that look like actually?
Yeah. So I mean, I guess why are the operating costs so low?
Yeah.
Maybe that's the first question.
Yeah, sure.
But and the reason is, like, if you look at the top cost categories for a hydrothermal project, and the EGS would be similar, I assume. And usually the first one is that you have all of these injector well redrills, or you have this kind of consistent. Sometimes it's not really categorized as an operating cost, but it's an ongoing injection of cash to redrill injectors, because they get plugged, or they get scaled, or they eventually corrode, or so you have this kind of well replacement cost. That's usually number one. Number two will be the pumping associated with these projects. So the cost of installing these large downhole pumps, and installing them requires a rig and multiple days on that rig. The pumps are hundreds of thousands of dollars themselves. So that'd be cost category number two. So
I understand, sorry to interrupt you there on cost category number two, but I understand that you've proven the thermal siphon.
We've proven the thermal siphon. So the point is, we kind of inherently eliminate these entire cost categories. We're not injecting into a formation, so we don't really have any need to, or any risk of an injector well redrill. We don't have pumps. We operate on thermal siphon. We don't have the electricity associated with those pumps. We don't have the water treatment. So a lot of these cost categories that would be in a, the top 4 or 5 in a traditional project, we just inherently eliminate. That's why the OpEx is so low. So, and we look at it, on a levelized cost electricity base. I'm sure you're
for sure
familiar with that, and probably a lot of the audience is familiar with that. But you essentially take your cash flows forecasted over the life of an asset, and then you discount it back. And then we look at LCOE, how much of our LCOE is associated with capital versus OpEx. We're 80 or 90% capital and only 10 to 20% OpEx. And you go look at, say, EGS or traditional hydrothermal, they're more like 50-50. If you go look at natural gas, it's it would be like 10% capital, 90% operating, because all your cost is in buying the gas. Natural gas power plant. I mean,
Yeah.
So yeah, ours is definitely, it's on kind of on one end of that extreme where it's all upfront CapEx and low predictable OpEx and operations.
Yeah. I mean, those are all really, I think, great examples of why a closed loop is advantageous from the operational perspective. What about from, say, a public perception perspective? Geothermal, there's talk about induced seismicity with geothermal. There's talk about, fracking if you're doing an EGS style project. There's, seismicity issues even with conventional if you're re-injecting into a reservoir. Like, how has public perception been in Germany for this, for the project?
I mean, I think it's a critical kind of parameter in getting projects actually built.
Yeah, stops projects.
And especially in Germany, I mean, it's a place where you need to have local kind of stakeholder acceptance. You need to have local social license, and you need that at the town level, at the neighbors level. You need that at the state level. You need that at the federal level, and without it, you're just not getting anything built. And there's a lot of power in protest and a lot of power in opposition, and it kills projects. And it's killed many geothermal projects. I mean, geothermal in general is obviously pretty good, any type of geothermal, because it solves some of the main problems in Germany, or in Europe in general, which is climate change and energy security. All geothermal forms have those benefits, but I think it's been important for us to show that we don't have the huge water loss, the huge water use, and we don't have the same induced seismicity risk. Those are the main issues that are perceived by local stakeholders, and we kind of mitigate those issues. So I think that's been important for us to get, and for our partners, which are licensed in our technology.
Yeah, no, for sure. I mean, are there big differences, say, between operating in Alberta and operating in Germany that you notice off of that?
Yeah, I think so. And I think the people are people. They're very similar.
Yeah.
But I just think Alberta has this long history of being adjacent to heavy oil and gas operations, and it's just accepted socially. That's not the case in Germany. That's not the case in many European countries. And especially, our market, as I mentioned, is district heating. To do district heating, you have to be adjacent or within urban cities and towns. So you're not, out in, 2 hours south of Grand Prairie or something, right? You're actually directly within a town or a village or a city or an urban area that's got, hundreds and hundreds of years of history. So you can't, you need to get by it.
Yeah. So talk about district heating. I think that's something that maybe the North American audience, except maybe those in Idaho, don't appreciate as much.
Yes.
But how much are you relying on the district heating component of geothermal, and say, are you building district heating networks? Are you relying on existing district heating networks? Like, I think it was Austria announced like something like 22 billion towards the expansion of district heating. Like, how much of that market are you looking to penetrate?
Yeah, I mean, it's a huge market in Europe. I might have these numbers a little bit off, so don't quote me, but I think about something like 50% of the emissions in Northern Europe, and 50% of the energy use is for heating. Right?
Yeah,
and it's probably similar in Alberta. The way that we have it here in Alberta, and a lot of North America is the same, is that you have it's supplied by gas, right? And you have gas. Individual homes have gas boilers, right? Individual buildings have gas boilers. That's how we do it in North America. But in Europe, district heating is prevalent and growing and much more prevalent. And the way it's done is you have essentially a centralized boiler, and then you have hot water that's distributed to individual homes, businesses, commercial buildings. And so a lot of cities, especially the more east you go in Europe, partly, especially old Soviet Union countries that were centrally planned, they're all, even small towns, all have existing district heating systems. Wow. And, they have this centralized boiler, and that's powered by coal or natural gas.
Yeah.
And so forever, we basically replace the energy source at a centralized boiler. So it's a pretty easy way to plug into an existing energy system.
Yeah.
But there's also, there's a lot of varieties of that. We're also working on projects where local utilities are building brand new district heating systems as well.
Yeah. Yeah. I mean, when I first started covering geothermal, and then started looking into Europe, to be honest, I was surprised by how much district heating there is. And it's just not something you think about coming from Canada or even North America. I mean, in most parts, except for Idaho, Boise, Idaho.
Absolutely.
Where you don't really think about district heating networks and how that's just such a big thing elsewhere.
Yeah, and it's not really, it definitely does not, I mean, North America is much more spread out.
Yeah, it's a good point.
In terms of, like, you need to have more an urban area for it to work. There is district heating, like in Toronto, there's district heating in downtown Toronto. I think even Calgary has some.
There's one building in Calgary. If you look on our platform, you'll see like 50 well bores smack in the middle of downtown Calgary. And you're like, what is that? You're like, oh, it's a building heating system.
Yeah, cool. Yeah, but it's a big part of the, and I can't remember the exact percentage of the heat market, but it's a big part of it. So this is a market, it's well over $40 billion a year in terms of district heating market.
Yeah, that's really cool. We're 42 minutes. Keep talking forever. Yeah.
Already, wow. Yeah.
Audience, we haven't forgotten about you. I'm gonna answer your questions in a second here. There's one more question I wanted to ask you, which is the biggest conversation topic in energy today is around AI and AI data centers and powering those. What involvement do you have in that at all?
Yeah, I mean, maybe I would just describe our business model that, we're in the near term, we're developing and working with partners, and we're licensing technology and working with operating partners in Europe in the district heating market. That's happening this year, that's happening next year, and so on. In parallel with that, however, we have a technology development program to go deeper and hotter, as I was mentioning. And essentially, we have clear line of sight to deliver low cost, well below $100 a megawatt hour electricity in an average geothermal gradient.
Yeah.
We have clear line of sight to that. And that is something that's very attractive.
So in a steep geothermal gradient, it's way better.
Well, in a steep geothermal, the interesting thing about what we're doing is, we don't really want to go to that steep geothermal gradient. We want to go where the customer wants it,
of course. Yeah.
And so it's really about that difference in approach. But the way I describe, we have Microsoft as an investor. This is public information. We're talking to other hyperscalers, and the way I would describe it's a fast changing market, but they have a huge need for power, and that need is very acute in the next 3 years.
Yeah.
And 3 years, they're doing anything they can, but things like what we're doing, even EGS will be able to make a little bit of a dent in that. But it's essentially existing standardized commercial technology that can scale today.
Yeah.
We're not going to really be able to make a dent in that 3-year time frame. But when you talk about the 2030 time frame, which it's an ongoing problem, and there's a lot of money going into that. And we consider our competitors we look a lot at small nuclear modular reactors. Fusion, there's like almost $10 billion have gone to fusion in the last decade.
Yeah.
EGS, other forms of geothermal. There's a ton of money and a ton of demand pull for these kind of carbon-free, dispatchable systems that can scale in that 2030 timeframe. And so we're definitely in that mix, and we think that's a huge part of our future.
Yeah. I mean, I think that's a thread we hear all the time is like, you need power, but time to power is a huge component of that. And you can't wait 10, 15 years for nuclear to get built, although we'll see if that gets sped up on some of the executive orders in the United States. Yeah,
it's not easy to speed up, even with a change in policy. Yeah.
Whereas if you, I think, had the right policy in the United States, for example, to permit some of these projects more quickly, like you could probably do, from first concept to first power in like 3-4 years, maybe.
Oh, yeah, much faster. And the way that our system works is, we build into modules, we build loops and bring them online.
Yeah.
So we actually can scale up in kind of smaller chunks that combined are a huge size project. In fact, pretty much all geothermal is like that. It's like an oil and gas, a shale pad. You drill one pad and drill another adjacent pad, and you can scale up in these chunks. And as an overall, it's a large output. So I think that's a huge advantage that all type of geothermals have on nuclear. Because when you look at nuclear, you're talking about huge capex, huge risk of overruns. And it's like this one big mega project. You can't really build it in these modular.
Well, they even talk about modular, and that's talking 300 megawatts.
Yeah, that's the small
modular reactor, right?
And it's years of construction. And it's stakeholder concerns are also difficult there.
Yeah, no, that's really fascinating, and I think I could ask you questions for 5 hours here.
Yeah, I'm sure we can. I'm surprised the time's flying.
We don't have 5 hours.
Okay.
We've maybe got 14 minutes left, and
okay.
Promised that we'd answer some audience questions. So let's do that. Let's see here. You can see the questions. Well, I looked at the questions. There's one that I think is pretty good, just because I like to help young engineers and geologists get into the space or understand how they can. And I pulled it at the beginning. And so while you answer this, I'll look for some other questions here. There's like, I don't know, close to 50 questions here. So sorry, we won't be able to get to all of them. But what are the technical skills that will be needed in the future energy sector with geothermal energy, say, involved for a young engineer? I think that's right up your alley.
Yeah, I think I think what is needed, it used to be that you could have, say, like a 40-year career and you would be, a drill bit designer, or you would be a, SAGD reservoir engineer. And I don't see that happening. I think it's important to be able to solve technical problems from first principles. So have a good understanding of physics, of engineering principles, and be able to look at problems. And there's always going to be opportunities for improvement and challenges to solve, and being able to apply first principles and engineering tools, basically software and AI is only going to accelerate that. Being able to apply software, AI to engineering problems, real world, real life engineering problems, not digital problems, and being able to solve those. I think that's a transferable skill set. I think that's what we look for. That's what we need. And it definitely helps to have some niche where you have some background expertise in, whether it's, wellbore design or thermodynamic modeling or whatever. That's what I would say.
Yeah, so fundamental engineering principles.
Yeah,
I'd say the same goes for geoscience as well. As it doesn't matter what kind of geology you're doing, whether it be petroleum or whatnot. The skills are 100% transferable.
Yeah,
maybe not 100% transferable, but very
transferable. And just having an open eye and being able to solve problems and work with people.
Yeah, working with people.
Yeah, totally.
So there's a question on thermal modeling and sort of thermal capacity and availability. So the question here is, how can you reliably model thermal capacity available for decades of thermal cycling? And I think I know part of the answer there.
Yeah, I mean, I guess the way that we do it and the way that, there's been a lot of third-party published papers by national labs, by government research organizations in Netherlands, in Canada, in Germany. There's a lot of third-party stuff out there, and basically they all use an approach, a simulation approach, and that's the way to do it. Is you need to build a kind of physics-based simulation approach where you discretize the rock and the wellbore, and you just calculate the physics in a series of time steps. So that's a computational fluid dynamics or reservoir simulation. That's what they do. That's what it is. And we just apply that same approach. And really the math and the physics, there's no error in the math and physics.
Yeah.
historically the errors in the inputs. Right?
Yeah, totally.
Like you don't know what the rock's going to look like far away from the well. But in Ever's specific case, in closed loop, it doesn't matter. So that's why it's so predictable, because the inputs are well known.
Yeah. I mean, way fewer variables, like as
Yeah.
opposed to say a conventional or even EGS style system where there's just so much variability.
Yeah.
And so what the fracture network looks like, or where the water flows through the fracture.
Yeah. What's it going to look like this year, next 10 years?
Yeah.
Is that water going to break through? Is it going to go into a different formation, different zone? All of these things are very difficult to predict. And that's, one of the, of course we have a lot of disadvantages as well. Ours is all upfront CapEx. There's some disadvantages with that, but it is predictable and reliable.
Yeah, I'm sure it is probably one of the most predictable, actually, in that sense. And you've also got a pilot to back some of that, to guarantee some of that predictability.
Yeah,
you've modeled it already, and you're seeing the results and matching those with the models.
Yeah, absolutely.
Yeah,
exactly. And that was huge to convince, convince customers, convince investors, convince partners.
Yeah, for sure. It's a cool question, because I always think about this with geothermal, and I think we're seeing it with, say, supercritical geothermal. But where are the limits? Like how deep would you actually want to go? Like, is supercritical the limit? Do you go much deeper than supercritical? Is there any point in that? Are there, say, technical limits to pressure? Like, can you keep a wellbore open at a certain degree? Like, at some point, the rock gets so plastic that wellbore just close.
So all very good questions. I guess the truth is nobody really knows.
Yeah.
Okay. We spent a lot of time looking at this exact problem. Right now we are designing and building and prototyping a drilling system that can go to 15 kilometers depth. 15 TVD.
I mean, put that in perspective. Like, what's the deepest wellbore in the world?
12,
like,
roughly 12.
12
is the deepest
kilometers.
TVD. Yeah.
Oh wow. Okay.
Yeah.
We're talking about world record.
We're talking about world record. I mean, MD is not the world record. There's wells today that are like 16 kilometers MD.
For sure.
Actually, our wells in Garrett's Reed, if you count it from as one whole loop, I think we might have some kind of record there.
I'm sure you do. Yeah.
It's over 16K for sure.
Wow.
But yeah, so that's where we're going, and we don't see any fundamental limits. We don't see any limits on the drilling system. We don't see any limits on temperature. So these are well over supercritical temperatures. We don't see any limits on casing, operations. The most unknowable one is geomechanic limit. But basically the way we're looking at that is there's two challenges. One is drilling. Can you keep it open during drilling? And we're confident you can with the right fluid design. And the second one is, can you keep it open over the life of the project? And and we're confident there as well. So we don't see down to that limit, but there's some other companies are talking about 20 kilometers, and there's, what's the true limit? I'm not sure.
Yeah. I guess we don't know if we've never drilled that deep.
Yeah, exactly.
I guess in terms of drilling deep, like one question that always comes up in my mind is, how do you actually the downhole tools? Like if you get into 375C, like how do you actually keep that cool?
Yeah, so the way we keep it cool is we use insulated drill pipe. I mean,
insulated drill pipe.
We've been doing that for years. We pioneered that technology.
Cool.
We're doing it at Garrett's Reed.
Yeah.
Even at Garrett's Reed, it's very difficult to keep things cool without insulated drill pipe. And the way it works is, I mean, it's kind of, you can imagine it's like a thermos. You put in cold drilling fluid at the surface, and it just stays cold. It exits the bit, and it envelops the whole bottom hole assembly in a turbulent flow of cool fluid. And then as it comes up the annulus, the fluid flows up the annulus, it heats up. But you can keep the whole wellbore cold with this kind of insulated drill pipe and active cooling. So you go back 5 years ago, people were working on kind of space age electronics, so non-silicon based electronics to handle these higher temperatures. And I think that's all kind of gone away, because with active cooling, you can solve the problem.
Yeah. Do you think we'll need laser drilling to get deep? Or
I think there's a lot of interesting things out there. Okay. I think some of it's never going to work. Some of it's interesting and could work, but drilling technology, like really new novel drilling technology, takes a long time to commercialize.
For sure. Yeah. There's a lot of really cool drilling techniques out there that are developing, and I'm excited to see them. Maybe take two more questions. One of them is around rock pipe, because I find this interesting,
Mm-hmm.
not using casing. Is there actually maintenance involved in the sort of in the rock type itself?
Yeah.
And are there differences in maintenance for temperature? Like if you start drilling into these really hot temps, is the rock pipe going to work better, or is it going to be harder to maintain?
I guess thinking about temperature first, I mean, the chemistry that we use has been proven in other industrial applications to well over 600 degrees Celsius. So I don't think temperature is an issue. It's not going to change with temperature, and that's a kind of not in a geothermal setting, but in other industrial settings that's been proven. So I'm not concerned about that. But I think in terms of maintenance, I think it's probably likely. We operated Eavor for 5 years without doing any real maintenance. We saw kind of a continual decline in our leak off rate over those 5 years. But the way that we plan to do maintenance is that it's all kind of fluid-based maintenance. So we just add additives that can continue to seal or improve the seal within the working fluid, or as slugs that we transfer through the working fluid. So it's not an expensive maintenance. Anything that when you do wellbore intervention, so you're going in there with a rig or a coiled tubing unit or anything like that, that becomes very expensive very fast. But a fluid intervention is relatively cheap. So that's kind of our plan, but we haven't had to do it, at least at Eavor.
Oh, cool. Wow, that's awesome.
Yeah.
So it's not very little maintenance.
Very little
and
maintenance.
if maintenance is required, it's very cheap and non-invasive, essentially.
Yeah.
Cool. Maybe one last question to close it off. Like, what are you most concerned about for, say, the scaling of your geothermal projects? And then, and on a positive note, what are you most excited about and optimistic about?
Okay. It's a good question. I guess the thing I'm most concerned about is, I just put it in a bucket and I'll call it just like execution and practical things. I mean, it's until the industry gets really big and really scales large, it's difficult. Everything's difficult. You have supply chain bottlenecks, you have people bottlenecks, you have you're the supplier of your supplier of your supplier needs to be able to scale as well. So all of these are challenges, and then there's just a kind of delay in getting projects off the ground. You have to go through regulatory hoops, you have to get stakeholder approvals, and this is kind of hard, detailed, grinding. I mean, maybe that's the bad way to put it, but it has to happen, and there's a huge amount of practical effort and coordination work that has to go into scale. So my concern is just being able to do that. I mean, this pretty much the standard in industry, and I don't mean geothermal, I mean industry as wide. Like if you look at big oil and gas mega projects, big nuclear projects, big geothermal projects, they're always usually delayed, right? And there's a reason for that, because
we were talking about that with CCUS.
Yeah, they're just CCUS. There's hard to do them. But I think that there is this ability to once it becomes routine enough, and it just becomes proven and reliable, and then you can see in wind and solar that you can scale massively fast once it gets there.
Yeah, I think especially if you can modularize it.
Yes.
That's where wind and solar really shine.
Yeah, absolutely.
Cool.
Yeah. Oh, and then what was your
what are you most excited about?
I'm the chief technology officer, so I'm most excited about the new technology we're working on. I mean, we have a base system today that can compete in the European district heating market. It cannot compete in the North American power market. Yeah. And it's not intended to. But the technology we're working on, like, we have this clear line of sight to make, affordable power anywhere in the world. This is a kind of a holy grail. There's nothing like it. Fusion is probably closest thing to it, and like, we don't see any fundamental technical challenges. We're on that path, and so I'm really excited about working on that and proving that up and getting that deployed commercially.
Yeah, it's cool. I've always joke with my colleagues. I mean, I'm a big geothermal proponent and always have been, and I joke that 70% of the grid will be geothermal by 2070. 70 by 70.
70 by 70. I like it. That should be the new motto.
We'll see if we get there.
Yeah.
But I really appreciate you having you on, and you coming to our office to speak with me about Eavor and your project in Germany. I think it's really exciting to learn more about it, to learn more about yourself and how you got there. Audience, really appreciate you joining, listening today, and offering so many great questions. I'm sorry we couldn't get to all of them. Maybe we can answer some of them offline here, which we'll have them recorded. But again, thanks for listening. Matt, thanks for joining me.
Thank you for having me. It's been a pleasure.
Yeah, and I guess everybody will see you in the next episode. So thanks.
Cheers.